extension is what's called virtual interrupts. So this is roughly how interrupt handling looks like on the ARM. The ARM has a two-part interrupt controller called the distributor and the CPU interface, and this is basically for configuring things, and this is for the actual interrupt handling. And by providing an extra copy of this one for the so-called virtual CPU interrupt interface, it's called virtual, but it's actually a hardware device, and it gets mapped into the guest. The hypervisor can simplify and make less costly the handling of interrupts. So if an interrupt comes in, goes to the CPU interface, invokes the hypervisor decides that this interrupt belongs to the guest, it can just re-raise the interrupt on the virtual CPU interface, and the guest can handle it, acknowledge it back to the virtual CPU interface, and the acknowledgement goes back to the distributor without invoking the hypervisor. So the hypervisor is only on the path when the interrupt comes in, but not when it's acknowledged. Okay, so this is basically what we have, and I'm not going to bore you with the details of how the hypervisor looks like. You can read that in the paper. It's not rocket science. So I'm just talking about the experience we have in terms of what's the complexity of the hypervisor and what's the expected performance. And keep in mind, performance we can only sort of guesstimate because we don't have a cycle accurate simulator. So hypervisor size is really reasonable estimate because we know we haven't implemented a few things, but then we have taken an existing code base and we could throw stuff out. So we know pretty much in the production quality hypervisor would be about this size, which is about 60% of the para-virtualization product which is offered for ARM by OpenKernel Labs. So not unexpectedly, the hardware support makes for simpler hypervisor because there's just certain things the hypervisor never needs to do. What also is clear here is that ARM is a much neater architecture, because if we compare the size of the hypervisor to what's the smallest hypervisor out there for x86, we see that the kernel code is about 2/3 of the size, but then on x86 you need a full instruction emulator as well, so they have QEMU in there, and that just blows out the code size. We don't need that in ARM. Instruction emulation is so straightforward. So, performance. Remember, this column is extremely dodgy. What we can measure is the number of instructions that need to be executed for virtualization. We can make some guesses about the instruction latency and compare that to what the power virtualization hypervisor does. Obviously, for a normal guest system, pure virtualization is much faster because the hypervisor doesn't get involved at all. The trap goes directly to the guest, and so there's zero overhead, whereas with power virtualization, you cover about 300 cycles for getting into the hypervisor twice. For other things, when we actually need to get into the hypervisor, then with the hypervisor using pure virtualization is much more expensive to enter and exit because these virtualization traps there's more processing that needs to be done than compared to the power virtualization case. And that also means that sort of similar story for interrupt handling, page fault handling. We get significant better performance with pure virtualization. Device emulation is likely never to use, at least for anything hardware performance critical, never to use pure virtualization. They will likely to be para-virtualized in the future because every device access 1,000 cycles. It's pretty expensive. World switch is an amazing difference. Basically, this is 10 microseconds for world switch on the pure virtualization case, compared to about quarter microsecond in the power virtualization case. So we're very keen to get our hands on hardware because there's obviously some really interesting trade-offs to play with. So what we learned is ARM is pretty neat in architecture, and the virtualization support they added is also fairly clean, and allows us to build a fairly simple hypervisor. And in certain respects, you can expect it to be much faster than on x86. But hypervisor entry and exit costs are expensive, and certainly work switches are quite expensive because there's a lot of virtualization state that needs to be saved. There's just a lot of extra privilege state that needs to be switched when you do work switch. It's, as I said, it's very dodgy numbers. They depend a lot on how the hardware is actually implemented in there. But we've got some experience with dealing with privileged instructions of various kinds on ARM, so we think these cases are roughly right. Anyone interested in more details? They're on the table, or talk to me.
Questions?
Do you have any experience about the IO virtualization, like SRIAV or IO-MMU from one side?
An IO-MMU is a platform feature, not a processor core feature. At the moment, ARM has only released the architecture for the processor core. However, they have announced systems complete chips that feature what they call the system MMU, which is essentially an IO MMU. And their approach again is very clean. They just use the same page tables. So you can figure IO to use the same page table as whatever operating system is running at the moment, which is a clean way to do it, I think. But we haven't been able to play with any of them yet.
So if you have IO MMU in place, your device can go down. Can you see that?
Not necessarily, because the IO-MMU really just translates EMA mappings. So basically, it means that you can use EMA safely, but the cost of accessing device registers doesn't change. So I think even with an IO-MMU, we will continue to use our virtualized device drivers.
Thank you.
So I didn't think about this before until you actually displayed on your slides. So when the hardware does the two-level table walk transition, is it any validation or checking, or does it just
it does the same as it does whenever it walks a page table. The page table themselves are virtual address space, so it means any access is validated by the MMU itself, which is really the main cost of having this two-step translation, because in worst case, with a two-level page table, you can get 4 page table logs if everything falls on all the mappings. And so the worst case behavior is actually fairly bad, but experience in x86 shows that the average case behavior is usually quite good.
So what is the potential impact of this virtualization support on ARM? So ARM is now using embedded systems, and I think few of them are using the virtualization techniques. So what's your idea about this?
Well, as I said before, there's a number. I've got a whole talk on why you want to use virtualization in embedded systems. There's some really good cases, good reasons why you want to do that. But ARM, of course, has a broader agenda. They offer Intel's turf, right? They're marketing their new high-end processor as low-end server processors. And they now, with the same extensions, actually, they introduced 64-bit physical addressing. And I heard rumor that the next release will give 64-bit virtual addresses, so they're really aiming higher. And I think that's a pretty significant part of their motivation of adding this hardware support, not just for supporting virtualization and embedded systems.
Any final questions for Gary?
Did you evaluate the scalability of virtual machines on large
I mean, when running multiple VMs on our platform concurrently, how is the performance?
With para-virtualization, scalability is not really an issue, at least with our hypervisor. I haven't looked at the virtualization extensions from the point of view of scalability, whether there's any issues. I couldn't answer that offhand.
All right, let's thank your note one last time.